Welcome, everybody. Everyone wants to get settled. On behalf of the library, I'd like to welcome you here this evening to the first lecture in this year's Outdoor Alliance. Pardon me. I know that's the name of the organization, but the name of the series is
Winter Outdoor.
Winter. Yes, I'm so sorry. Yeah. Anyway, I'm so sorry. We're gonna go back. This is the creative part of the program. I'm sorry. I just stumbled on my own prepared remarks. I'm sorry about that. So anyway, welcome to the Ames Public Library. This year, this is the first lecture in the series, a three-part series sponsored by the Outdoor Alliance of Story County, as well as Story County Conservation and the Ames Historical Society. So thank you very much to our partners. I'm just so thrilled all of you are here. I want to remind you that the library's mission is to connect you to the world of ideas through diverse and inclusive resources and programs. And we do welcome all program proposals, so if you have any ideas, please feel free to share them with me, and I'd be happy to work with you. This room is provided with an induction loop for the benefit of hearing aid users. To use, please switch your hearing aid to T. Also, I do have a hearing assist device that I can loan you, and it's in the back of the room. So if that would benefit you, just let me know. I'll be in the back of the room. We invite you to check out our table of flyers and our current issue of page 1, which I have set aside on the table. We have a brand new updated website. I hope you have checked it out. And on that website, we have a really lovely calendar of events. And again, I invite you to look there for everything that's happening at the library. At this point, I really do, though, want to turn it over to a member of the Outdoor Alliance of Story County, Bruce White, who will introduce our esteemed speaker. Bruce.
Thanks, Mary. Is this still on? Okay. You have to really get it up close. Well, on behalf, again, thank Mary and the Ames Public Library for being our host tonight. On behalf of the Outdoor Alliance of Story County, I'd like to welcome you here this evening. This is the third year we've done a series of winter presentations on a variety of outdoor topics in the past. As Mary pointed out, it's a partnership with both the library, the Ames Historical Society, and Story County Conservation. Last year we had 3 presentations, and we ranged from going down the Skunk River. We learned about the history of the Skunk River from north of here a ways. We also had a presentation on young birders, and we also had an interesting presentation at the end of our series last year on Stories of the Stones, which is actually a presentation on cemeteries, local cemeteries here in Story County. So we're really looking forward to our series this year. Glad to have Sam with us. I think, looking at the audience, I think Sam knows you better. You probably know Sam better than I know Sam, so I'll keep this introduction very brief. But Sam's going to be talking to us tonight about winter skies, constellation stories, and folklore, which I'm looking forward to the folklore part, Sam. And we'll explore that topic with him. And a little bit about Sam. Dr. Wormley earned his degrees in mathematics and electrical engineering here at Iowa State. He's retired associate scientist and principal investigator at the Center for Non-Destructive Evaluation and the Institute for Physical Research and Technology at the Ames Laboratory at Iowa State University. And for 17 years, he was an adjunct professor with Marshalltown Community College in astronomy. So we're looking forward to that. Sam is devoted to lifelong learner. I know maybe some faces look familiar, at least from OLLI, that Sam is a almost perpetual instructor at OLLI on a variety of different topics, from Apple computers to climate change, and as a variety of courses I wanted to sign up for. Never had a chance to get into his class, so a couple of them. But really happy to have Sam with us here tonight, and look forward to hearing what he has to say about our constellation and our night skies here this winter. Well, help me welcome Sam Wormley.
I would like you to imagine that you're outside under the nighttime sky, away from city lights. And you should also imagine that you're comfortably warm in boots and coats and mittens and hats and scarves, because it's a crisp, clear winter night. At least in our imagination it is. But if you go outside, it's really cold. The stars twinkle. And it's not an inconsistency in the stars that makes them seem to shimmer in the winter skies, but it's instability in the atmosphere. We look up to the stars through a wrap of cold air that shivers and shakes, and it's especially turbulent in the season of winter. You may also notice, at least I did on the farm where I grew up, that after a thunderstorm line would move through and the sky would clear, and you could see there was a shimmering or a twinkling of the stars then too. And that's because there were many different temperature layers in the atmosphere, and as that starlight came through the atmosphere, it would refract, and that refraction would be changing, and that's what accounts for the twinkling. What you have here on the projection is a planetarium program called Sky Safari, and I'm going to use that to walk us around through the winter skies. So if you look to the south, and this is a southern view, it's dominated by the powerful figure of Orion. And I have the lines drawn on Orion here, which show you, I guess they're called the modern lines, how we sort of visualize the character among the stars here. But what's unique about the Orion the Hunter? It's not only one of the most familiar constellations throughout ancient history and today, but it's the only one that has these three bright stars in the center which are easily distinguishable, and there's nothing else like that in the sky. These names of these three stars in the belt are Alnitak, Alnilam, and Mintanka. And they're Arabic translations of ancient Greek names that come to us from the time of Europe's Dark Ages, when astronomy was cultivated by the Arabs in centers of learning such as Baghdad. Many star names start with Al, which is the Arabic prefix for the. And so Alnitak means the belt. Orion is a good constellation to practice seeing colors of stars. In the right, I should have had a laser pointer. Do we have one?
Yep.
In the shoulder of Orion is that orangish red star, and it's called Betelgeuse, and a lot of people just say Betelgeuse, and it has a reddish hue. And in the lower right knee, the forward knee, is a really bluish star. In fact, the belt stars are visibly bluish. Now, have you got a question as to why the different colors? Okay. Is that Jeff's back there? Yeah. Good. The stars are either different kinds of stars, big, small, large, whatever, but the color tells you something about their temperature. And so Betelgeuse here is a red giant star. And that's a star, like our sun, only this one's much bigger, that's in the last 10% of its life. And so stars tend to fuse hydrogen into helium for the majority of their, for 90% of their lifetime. And when that helium starts to deplete in the core of the star fuses less and less and less. And so the energy being produced in the core becomes less. And gravity is trying to pull all of the gas of the star in toward the center. And so it starts to move into the center. And it's just like pumping up a bicycle tire. Have you ever felt the tube of the pump when you're pumping a bicycle tire, the air into it? It gets hot because you're compressing the air. And when gravity compresses the material of the star, it actually heats up that core. And that core eventually gets hot enough to do a secondary fusion process of fusing helium into carbon and nitrogen and oxygen. Carbon, nitrogen, and oxygen, and the original hydrogen, those are the necessary elements for life. We have to have those. So Betelgeuse is a nice big red giant star in the last 90% of it, or last 10% of its life. And down here, Rigel is a hot blue giant star, and it's not going to last very long. It'll probably last 2-3 million years at the most before it goes into its later phases in its last 10% of its life. So these things are really temporary. And if you live long enough, you'll be able to notice that. Well, the coolest stars are red. And if you go from red to orange to yellow to white and then to blue, that's from the least hot to the hottest. And our sun is a yellow star. It has an average temperature. It's got about 6,000 degrees Kelvin surface temperature. And our eyes have evolved on this planet under the sunlight so that the combination of the yellow-green, which is the most energy output is in the yellow-green part of the spectrum, and then the tails fall off a little on the red and the blue. Our eyes have evolved with sensors so that that looks white to us. And so white is a characteristic of animal life that has decided to give it a name and so on. Well, the hunter has two companions. This is the big dog, if I can get an outline of it here. And of course you get a little music in the process. So this is the constellation of the big dog, Canis Major. And the brightest star in Canis Major is called Sirius, and it happens to be the brightest star in our sky. Seriously. Well, I had to try. So it's considered to be the heart, and how all of these lines are drawn supposed to represent a dog. And so Sirius is the big dog, and Canis Minor, which is up over here, is the little dog. And what I'm trying to do is show you the constellation boundaries there. The big dog is at Orion's feet, and the more excitable little dog is up closer to his shoulder. Now Sirius is pretty close to us. The closest star is a little more than 4 light years away. And when I say light years, I mean how long it takes light to travel 1 year is what we call a light year. We define that as a unit of distance. Now, Bruce is maybe 10 feet away from me, and light travels at 10. It takes about 1 nanosecond to go 1 foot. So we're about 10 feet apart. So it takes about 10 nanoseconds for the light to get from your face to my eyes, and vice versa. So actually, I'm seeing you in the past, because I'm seeing you. And, you know, when I look at the moon, that's 1.3 seconds that it takes for the light to get from the moon to my eyes. So I'm seeing the moon as it was 1.3 seconds ago. And if I look at the sun, no, you don't want to look at the sun. Maybe at sunrise and sunset. There's a delay of 8 minutes there. It takes 8 minutes, a little more than 8 minutes for that light to get from the sun to my eyes. Okay, now Saturn, seems to me that's about, it's about 10 astronomical units away, and the Earth is 1 astronomical unit, by definition, from the Sun. So Saturn is 10 times further, and 10 times 8, so we got about 80 minutes for the time from light to get from Saturn to me looking at it. And then when I jump to the stars, the closest star, turns out that the light takes a little more than 4 years. So we call that about 4¼ light years is the nearest star. And Sirius, this brightest star over in the Big Dog, is 8.6 light years away. And that's about twice as far as as the closest neighbor star. Well, if the night is dark and a bright moon is not in the sky, unfortunately, if we were to go outside right now, the bright moon would be right above Orion and tend to wash it out. But if the moon is not there, then you can see this pale river of light going over the shoulder of Orion and down between the 2 dogs. And that's a myriad of stars, each too faint to be seen with the unaided eye, but together they look like this milky, they look like the Milky Way, because that's why we call it the Milky Way, because it looked like spilled milk in the heavens. And the name Sirius, well, that means searing or scorcher. And it's appropriate for a star that shines the brightest of them all in our sky. And because of its brilliance, Sirius is the champion of all the twinklers. So on a twinkling night, when you look at Sirius, sometimes it might look a little bit red or a little bit blue and jumping back and forth. And so that's the refraction in the Earth's upper atmosphere that's causing that. Now, because Sirius is the brightest star in the constellation Canis Major, we call that the dog star. And it turns out that Sirius and Procyon, which is the brightest star in the smaller dog, they are both binary stars. That means they have a companion that's going around them. And the companion going around Sirius and Procyon is a white dwarf. So we have a star in its major, in what we call on the main sequence, happily fusing hydrogen into helium. And the 2 companion stars have already gone through most of their life cycle and blown off their outer layers, and you just have this little dense core. It might weigh about the same as a star, but it's only the size of the Earth physically. And a white dwarf is made up of mostly carbon and oxygen that were created by the star that they once were. In June and July, the sun is just above Orion in the constellations of Taurus and Gemini, and so it makes it inaccessible. We can't see Orion or the dogs in the summertime night sky. The sun hides those constellations. So I don't know how far back in time we have to go, but the Egyptians used to try to see when could they first see Sirius in the dawn sky. Because that tended to coincide with when the flooding was going to start on the Nile River, and so it told them the season of prosperity was on its way. The Earth spins on its axis, and that axis is pointed toward the North Pole star right now. But over a 26,000 year cycle, it actually precesses around like a top. And so about 4000 BC till now. We've got about 6,000 years out of that 26,000. And so the sky has shifted with respect to the sun, and that means that's no longer true when people first see this Sirius rising in the dawn. That no longer coincides with the patterns of the Nile River. Let's go somewhere else. Let's look at the north, and you can see the Big Dipper over here and the Little Dipper here. Can you see those lines? Does that barely? So you have to do just like if you were outside. You have to imagine what they look like. Maybe I can touch that a little bit and make it better. Okay, this is the Little Dipper. Okay. Yeah. And the Big Dipper. And the Big Dipper is really quite a bigger constellation, Ursa Major, than what we would anticipate from just the Dipper. When I was growing up on the farm, I used to look at the night sky and I would see this little pair of stars. And there's a pair of stars here and a pair of stars down here. And the Native Americans and the Greeks thought of this as a large bear, and those were the claws of three of the limbs of that bear. And that's where those come from. But other civilizations saw all kinds of different things. In England, this was a cart. Let's see, Wayne's cart, Charles's Wayne, something like that. So this was a wagon with a handle on it. And the Egyptians thought of this as a very complex pattern of a crocodile and a hypopotamus and strange. Anyway, you can see those patterns of stars and carvings with the animal outlines in ancient rocks that have been carved upon. So the Big Dipper, I'm going to make this, I'm going to get rid of this and make this bigger. We have 4 stars making up the bowl of the Big Dipper. And here, the middle star in the handle is called Mizar. And it has a little companion star. And that star's name is Alcor. Not Al Gore. Alcor. And the tale is that Egyptian soldiers were considered to be fit enough visually if they could see that little star, which most of us can, right next to Mizar. If I make that bigger, you can see there's actually a 3rd star in there. So I think Roger Berger is one of the people that has had conversations with me, and he asks the question, are those 2 stars gravitationally bound to each other? Do they actually orbit a common center of gravity? And if they do, the period of that orbital pattern is over 100,000 years, so it's not something that we can verify. But it is thought that they might be gravitationally bound because they're at the same distance and they're fairly close together in terms of not very many, they're less than a light year apart. And so we think that they may be a system, a binary star system. Okay, the 2 leading stars of the Big Dipper are called the pointers, and they actually point up here roughly to the pole star. And this is something you may have learned as a kid, to be able to identify the Big Dipper and follow those pointers to the North Star, and then you would know where north is. So everything rotates around this North Celestial Pole and South Celestial Pole. And so the Dipper is coming up, and by summertime it will be kind of overhead, and on the opposite side of the pole star, this W, Cassiopeia, will be down in its place. So Cassiopeia and the Big Dipper, the bowl, are on opposite sides of Polaris. So this is what we see in the north. And I have flashing here the constellation Draco. And Draco has a sort of a trapezoidal existence here. And there's a pair of double stars there that I was able to see as a kid that always thrilled me. It was just so I could look at it. In the summertime it was almost overhead, and I could look up there and see that double stars. And I think I can show them to you here. Getting that to have enough distance it's not. I'm not going to be able to do it, but that's the head of the dragon. Okay, now I'd like to show you what thrills me every fall. I'm going to go to the east, and I'm going to back up the time. Oh, by the way, here's a comet. So northeast, east, and we're going to change the time, and I'm going to change it to 1 hour, and I'm going to back up in time, 1 hour, 2, 3, 4, 5, 6, and 7. The first thing that rises in the eastern sky, it's actually the northeastern sky, in October, November, December, in the early evening, is this Pleiades. The Pleiades is called the Seven Sisters. And astronomers through the ages would try to outdo each other by saying how many could they see with their naked eye. For most of us, we can see 5. Some people can see 6. Some people can see 8 and 9. But the Pleiades is a small cluster, about 400 light years out in our galaxy, and it's relatively young. And so most of its stars are hot blue stars. Older stars tend to be yellowish. And the Pleiades is a cluster. There are probably 1,000 stars born out of the same cloud, and I can't tell you how long ago, but probably within the last few million years. Because these are pretty big, bright stars, and they only last a few million years. So that's about how long ago within the cluster. And of course, it takes 440 years just for the light to get to us. So, the Pleiades is a kind of a baby dipper in the sky and one of the favorite constellations in antiquity. So, an hour later, the Pleiades is much higher now. Oops, I think I went too many. The moon is in the way, but here's the star called Aldebaran, right here. and it follows just under the Pleiades. And you know what the name Aldebaran means? It means follower of the Pleiades. So Aldebaran rises, and then about an hour later, we're going to see the belt stars of Orion come up. So here they are just crossing the horizon. The green line represents the horizon, and you're not supposed to be able to see anything below it. And then after Orion is in the sky, the next is going to be Sirius. So you've got this pattern over about a 3-hour period. First the Pleiades rises in the east, and then that's followed about an hour later by Aldebaran, the follower of the Pleiades. And then roughly an hour after that is Orion, and the 3 belt stars are in that line. And then following that is Sirius. In the western sky, things tend to be setting. So we have, here's the summer triangle. It's made up of Deneb, and the constellation is Cygnus. Deneb is a swan, and Deneb is in the tail. Cygnus is a swan, and this is the head of the Cygnus, and the wings are here and here, and it looks pretty much like a flying bird. It really does. This is called the summer triangle because it's very prominent in the summer. Deneb and Altair and Vega make up the summer triangle. In fact, you should see some red lines that are connecting those 3. So that's all sinking in the west this time of year, while Orion and the dogs are rising in the east. And as the belt stars come up in Orion, they come up vertically, and by midnight they're pretty much horizontal, and by the time they set early in the morning, they're going to all set at the same time, because they will be definitely horizontal as they hit the horizon as they set. You see some of the planets running around here also. You can see that the sun is already set. Mercury and Venus are below the horizon down here. The summer triangle will follow. Now if I move forward in time, 1, 2, 3 hours, 4 hours, and get over here to the south, and actually in the southwest, and if I get further, here you can see the 3 belt stars just about ready to sink below the horizon, and they're now laying this way instead of vertical as they came up. So I go back to now, and this planetarium software knows where I am on the Earth, and it knows what time it is, and so this is what the sky really looks like right now. Now here, these circles represent the shadows of the Earth. And if I set this to day, today's, and back up, 1, 2, 3, 4, and I'm pretty close, and now I'm going to change that to minutes, and I'm going to make that a little bigger. Whoops. Stop. I need to center that. So I'm going to pick the moon, and I'm going to center on the moon so it'll stay in the center, and I'm going to turn it on. And here's what happened on Sunday evening. And I'll run it backwards. And you see it turns blood red when the light is totally blocked. I'm going to stop that. Push it forward just a little. And stop it. So, does anybody know why it's red? You would think that if you're in the shadow of the earth and no sunlight is falling on it, it would just be dark. But if you were standing on the moon and you could look back at the earth, what you would see is a body that's quite a bit bigger than the moon, and you would see the thin little atmosphere all the way around the earth, and it would have this red tinge to it, just like on a sunrise or a sunset. And it's this reddish light, it's called Rayleigh scattering, that projects along the line from the sun. And so it's that red light and that little ring around the earth that actually falls on the moon and makes it look blood red. Now, if you had an eclipse where the moon actually passed dead through the center, it would be a uniform red. But since it's close to an edge, it tends to be lightish on one side, near the edge of the shadow. And I could actually back this up. I'm not going to do it, but I could back this up to August of 2017, and you would see the moon go right in front of the sun, and it totally blocked it out. And I got to see that, and I want to describe that to you because that's a pretty important event in my life. We go to Colorado every summer, and the eclipse was in August, so we decided to have our John out to Colorado in August because we thought, the skies, are they more likely to be clear in the western states than they are, say, in Nebraska or Missouri? And so we took a chance. We were out there, we got there 2 days before the eclipse, and then we started to hear about the news reports about how much traffic was expected and how much delay and all of that. And I was almost ready to bail out and just watch it on my computer. And then I thought, I'd be denying my wife and my brother-in-law an experience here. So we set out about 3 o'clock in the morning. And we were going to drive up into Wyoming to this little town, which was on a reservoir, and the town had 203 people. So we thought this would be a good place to go. When we got 2 miles from the turnoff of the interstate, the cars to turn off were backed off, and there were already 8,000 vehicles swamping this reservoir in town. And so we decided to move on. And in fact, the gas tank was getting low, and so, I worry about that kind of stuff. And about 12 miles later, we came to a truck stop. And I knew I could get gas in there. And the cars were backed up from the pumps, about 8 or 9 vehicles. But we got gas, and then we just decided to stay there because the eclipse was going to go right over. And so with about 300 other people, we shared the experience of a totally clear sky. The first thing that happens, maybe 45 minutes before totality, is that if you have solar glasses so you can look, you see the moon is just starting to cover the edge of the sun, so it's just a little notch out of the side. And then that gets bigger and bigger and bigger and bigger. And about 11:44 and 45 seconds, the sun blinked out. And it was just amazing. People clapped and made noises, and they quit flying their drones. What I took with me, I said, I'm not going to photograph this. I'm just going to experience it. So I took a pair of binoculars with me, 7x50, and I have a little stand so that I can mount them looking through a first surface mirror up at the sky. So it's like looking through a microscope. So it's pretty comfortable. And I had solar filters on. And so I could watch the progress of the moon coming across the sun. And then when it blinked out, I took those off, and it was amazing to look at that total eclipse through those binoculars. You could see all the streaming of corona billowing away from the sun, and you could see these red prominences that looked like flares around the edges. And what you could see with your naked eye, well, I mean through your binocular eye, was as good or better than any photographs I've ever seen. It was just tremendous. You know, and this was only going to last a little more than 2 minutes. And I got my companions up there to look through there, and somebody says, "Did you notice the sunset?" And I looked all the way around, and it looked like a sunset in every direction. And then, bingo, a big bright light shone, and that was the little edge of the sun uncovered is like a huge light. And so I put the filters back on the binoculars and started to watch it, and everybody started packing up to go home. It took us about an hour to get out of that truck stop, and it took 14 hours to get back to Evergreen, Colorado. Bumper to bumper traffic. We tried going through little towns, going around the interstate. It was everything, bumper to bumper cars everywhere. So there are probably more than 1 million people leaving that part of Wyoming going back to Colorado. And you know, I really have to give credit to all the sheriffs and the deputies and the highway patrols that got us all home safely. And the other thing about that experience is that people were polite to each other. They had shared an experience, and if somebody wanted to cut into a line of hundreds of cars, they made room for you. It was wonderful. So I'm going to go back to now. And here's where the moon is in the sky. And this line going through it is its path that it will take. And you notice this path wobbles? And that's because the Earth and the moon are orbiting a common center of gravity, which just happens to be about a quarter of the diameter of the Earth, or a quarter of the radius of the Earth under the surface. So that point is actually inside the Earth, and the wobble effect is there because the Earth rotates on a daily basis, and you see these patterns, and eventually the moon will get close to the sun, and it'll miss it this time because it's not that close. Let's see how close it's going to be. Well, I don't know if you saw that, but the path of the moon will definitely miss the sun and will not have a solar eclipse that we can see. So, why are these eclipses? Why did they even take place? The orbit of the moon is tilted with respect to the orbit of the Earth around the sun by about 4 to 5 degrees. And so twice a year, those orbital paths intersect each other, and when that intersection takes place, and the sun and the Earth and the moon are in a straight line, you get one of the two eclipses. You either get a solar eclipse, where the sun light is being blocked by the moon, or in the case of a lunar eclipse, where the moon is actually passing through the shadow of the Earth, as did last Sunday night. People all over the world, even near the poles, have experienced these things ever since humans have been alive. I want to tell you what happened with Columbus. Columbus had come to the New World. I don't know if it was his first trip. It was probably a later trip. But he sailed north into what is now Jamaica. And he beached one or more of his ships. And he couldn't, they were in the sand and he couldn't get them out. The tide was not high enough to get them out. So he was having to wait for one of the other vessels to come. And during those months, the Native Americans that lived there were supplying him with food and drinkable water and so on. And after about 2 months of that, they got tired of it. And Columbus had navigation charts with him. They knew how to sail the seas, and they could figure out where they were in terms of north and south from these charts and making sightings on the sun. And there was also an almanac in there, and it predicted that there would be a total lunar eclipse occur in that part of the world. And he knew that was going to happen. He hoped that the weather would be good so it could be seen. And 3 days before that lunar eclipse took place, he told those Native Americans that his God was angry that they were no longer taking care of he and his crew, and that if they didn't help him out, he was going to make that God would take the moon away. Well, I don't know why these Native Americans had never seen an eclipse of the moon before, but they thought that was ridiculous. And so on that third night, all of a sudden, there's this little bite out of the moon that's starting to get bigger and bigger and bigger. And these Native Americans are getting panicked. And about an hour later, when it started to become blood red, they went to Columbus and they said, "We will continue to help you if you restore our moon, if your God will restore the moon." And Columbus waited just a little bit of time and waited till he knew the eclipse was going to start to not be total anymore, and said that his God was pleased and that he would restore the moon. This is a true story. This really happened. So, by knowledge of knowing when that was happening, Columbus used it to his advantage. I don't know that that was good or bad, but that's what happened. So I use this software to predict things in the sky, to be able to see what's rising, what's setting, what's overhead, look for comets, and so on. And I would love to hear any kinds of questions you have about the night sky. There's so many stories about all these things. And in fact, there's a whole book that Dover Publications put together called the Lore of the Night Sky or something like that, which is just full of stories about each of the constellations. And I didn't bring it because I didn't think to do that. But I do want to recommend a book to you. There are several books. There's an Irish guy named Chet Ramo, R-A-Y-M-O. And the first book that he published was called The Soul of the Night. And I think chapter 3 was called The Follower of the Pleiades. And that's how I happen to know about that. And he writes, the book, each chapter is like an essay, and it's really good. He's written many other books, and he's very eloquent with how he describes the sky. He's knowledgeable as an astronomer, he's an excellent writer, and he's even a theologian, and he's a good resource. So it's called The Soul of the Night, or anything by Chet Ramo would not disappoint you. Now, you folks are associated with, what do you call it, the Outdoor Alliance of Story County?
Yeah.
And do you have evening events where you look at the sky?
We don't. Not yet. You never invited us, Sam.
Wow. Well, one time I was asked to do the night walk out at the Conservation Center with people and talk about the night sky. And unfortunately, it was a night of a full moon. So the full moon pretty much washed everything out. But there was a ring around the moon. And that meant that there had to be some ice crystals in the atmosphere that would cause the right angle of refraction, so that ring had a diameter of about 22 degrees. It's about like the span of my hand outstretched. And what other kinds of things have you seen? Do you know what sundogs are?
Oh, yeah. It's all
Okay, again, refraction through crystal effect of ice in the atmosphere in the daytime, and so you see these sundogs on either side of the sun, and sometimes it goes all the way around. Have you ever been outside with a garden hose in a fine spray and seen a rainbow in the water droplets? And you can hold it in such a way that that rainbow becomes a circle?
I'm going to bring the lights up a little bit. Is that okay?
Yeah, that's good.
Okay.
Okay. Go.
There you go. I got it.
Yes.
Questions?
I assume that the red lines are.
You have to be pretty close.
I assume that the red lines are constellations. There are at least two in the upper right-hand part of that. And I just wondered if the program gives you the names of the constellations.
Let me turn the constellations on. Here are the lines for all the constellations. Can you see those?
No.
A little bit.
When I look at the night sky, I can't see them then
There are 88 keys on a piano, and there are 88 constellations in the sky.
That's a coincidence. Okay, on your software, when you had a constellation highlighted, when you went bing, bing, bing,
Mm-hmm.
and then there was a white outline around it,
Mm-hmm.
what is that? Because there are other stars contained in that white outline. How is that boundary defined? What does that mean?
Okay, by international agreement, and I think this happened in 1875, the astronomical community came together and they declared what the boundaries of the constellations would be. And so this is Pisces. Basically what you're seeing, these lines are the international boundaries, and because of the precession of the Earth around its axis, they slightly move, those lines slightly move with respect to those stars. So in the constellation Pegasus and Andromeda, that boundary has changed enough that the bright star near the Andromeda galaxy, I can't remember what the name of it is actually in a different constellation than when these boundaries were drawn.
So you understand that if you were to highlight the constellation next to it that has Alcaraz at the top, those boundary lines would be the...
They would fit with these boundary lines. So Alpharez here is part of Pegasus. And it may be that it's no longer part of Pegasus. See, it's outside the boundary. But the lines of the big wing of Pegasus That star is one of those, that's called the Great Square of Pegasus. And one of the really nice things about the Great Square of Pegasus is when you look at it, you're actually looking out through the side of the galaxy. And so it's sort of a clearer vision of outer space that's beyond the galaxy. Great Square of Pegasus is a nice tone. You see Mars is near here. Mars is the planet just after the planet of Earth in terms of its orbit from the sun. It's about half again the Earth's orbit out there. So the Earth is 1 astronomical unit from the sun, and Mars is 1.5 astronomical units. There's a constellation in the summer called Scorpio, and it has a big red star in the heart of that scorpion that's like Betelgeuse in Orion. And the word means rival of Mars. Antares means rival of Mars. Now, have you heard, here we are back at our eastern and southeastern sky with Orion and the dogs, and Castor and Pollux and Gemini up there. By the way, if I can show you those, Castor and Pollux, these lines are drawn by a guy named H.A. Ray, R-A-Y. Curious George. He drew modern shapes of the constellations, modern connecting lines. And so his Castor and Pollux, and I know you can't see it there very well because of the lights, it looks like two twins that are joined together. Whereas the old boundaries that came along before H.A. Ray's new modern lines didn't look like a pair of twins at all. It looked like a box or a refrigerator or an iPhone or something like that.
Do we know how the planets and stars came to be out there at all? What's the theory besides Big Bang?
Okay, besides the Big Bang. Yeah. Well, let's talk about our solar system, how it formed. There was a huge cloud of gas and dust, probably enough to make several hundred or maybe even 1,000 stars, that started to collapse. We met some kind of criteria called the Jeans criteria, which means that the gas is cold enough that there can be little areas where the density increases, and that serves as a sort of a nucleation point for gravitational collapse. And so most stars that are born in clusters of stars from the same big collapsing cloud of gas and dust. Now the gas is about 75% hydrogen and about 25% helium. And 2% of that in our galaxy in this time period is all the other elements, roughly 2%. So what happens is these things get fragmented, and each little fragmentation becomes a star. As the material falls in to these local nucleation points, that gas gets hotter and hotter and hotter and hotter, and it's still all falling in. And because of the conservation of angular momentum and the fact that we've got some random rotation, as things fall in, they tend to fall into sort of orbits around this center of nucleation. So when the sun, what became the sun, when that center of nucleation gets hot enough, it can start thermonuclear reaction, fusing hydrogen into helium. And when that starts to happen, the star is producing new energy other than the heat of just collapse that's going to become sustainable. And so the sun will settle down and come to equilibrium, happily fusing the hydrogen into helium at a specific rate, and the boundary of the sun will will become more definite instead of diffuse. But you have all this other material still in an accretion disk around this area, and that's dust and hydrogen and helium, and it will eventually, little pieces will freeze because they're away from the heat of the sun, and so we've got little grains of dust, and van der Waals force and electrostatic force will allow these things to stick together, and when they get big enough, like pebble size, they got just a little bit of gravity, and that might attract the next pebble and so on. And so you start to get this clumping of matter in this accretion disk, and what we find now is that Mercury pretty much swept up all the material in real close to the sun. And then Venus, the next little area, and then the Earth, and Mars, and Jupiter, and Saturn, and Uranus, and Neptune hasn't really cleaned out its area, and so there's a lot of dust at the same distance of Neptune and beyond, and this has become what we now call the Kuiper Belt. This Kuiper Belt is leftover material that has not coalesced into large bodies, maybe some small bodies, and it's pretty much an icy world. And what you need to know is the material that swept up to form the sun and the planetary nebula had a lot of water in it. If you remember, most stars, in fact all stars, create helium out of hydrogen. And then if the star is massive enough, like our sun, the secondary reaction is the helium fuses into carbon and nitrogen and oxygen. And if the star explodes, that helium, nitrogen, the nitrogen, oxygen, and carbon get spewed off and get collected into new planets, and new stars that are forming in their planetary systems. And so, two of the things that are very common are carbon and oxygen. And there's plenty of hydrogen around, so there's copious amounts of water throughout the universe. And our solar system has a lot of water. The cometary material, comets, are roughly 50% water. Asteroids even have water in them. And the planets, almost all of them, have a substantial amount of water. The Earth has twice as much water as is in all of the oceans around the world, inside, under the crust, in the mantle. We know that because we can measure radiation coming through. In fact, I think you can do penetrating radiation, and when that comes back up, you can see the spectral lines of the elements, and you can see the hydrogen, and you can see the oxygen in the same place, and it's water. And that's one thing that's very important to astronomers, is they put spectrographs on their telescopes. They don't look through them with an eyepiece. They put spectrographs on their telescopes, and they determine almost everything we know about the modern universe from the spectra of the light that's captured from galaxies and stars and planets and so on. Oh, like this? Okay, one more question? These things are planetary clouds, usually of glowing gas and dust, maybe heated up by a hot star, or cold condensed bunch of gas and dust. And so, everywhere in the Milky Way is littered with these things. And if you look around Orion, and you've seen pictures of Orion that show all kinds of cloud-like, billowy things. There are a lot of clouds of leftover material that's not formed into stars in the Orion area. Okay, we've got to finish.
Just so, Sam, real quick questions. Obviously, all of these names are Western, right? They either come from Arabic, Greek, Latin, this kind of stuff. There also were old civilizations in the East. Did they have I assume, different constellations? And do they still use those constellations, or has everybody switched to this Western system?
Well, it's not just Western. In fact, if you look at all the names of stars, you're looking at human history. I mean, you've got Chinese and Asian, and, as well as the Greek and European names. Of course they did, and so their names are different than ours. But it's the same thing.
Are the constellations the same shape, in other words, but different names for the stars?
Yeah, constellations look pretty much the same for tens of thousands of years, maybe 100,000 years. And so you can imagine that the first humans that looked at the sky saw other kinds of pictures than we do. And the ones that were codified in the 1800s with microscopes and telescopes and dippers and bears and all that sort of stuff. And when people were sailing the oceans, there's rudders of ships and sails and masts. And all of those things make up different constellations. And if we did it today, if we started today, we would all see different things. Maybe umbrellas and refrigerators and bicycles. And so it's all human imagination.
I noticed that Mark, the shoemaker leaving, because I recall the comic. Does this program show the paths of, like, Mars and the comets and so forth? Does this program show that?
This program will go back and forward in time at least 4,000 years with a lot of accuracy. It's got a billion stars cataloged. It has modern comets. And so we can look at eclipse events. We can go back and see what was considered to be the star in Bethlehem and all of those things. I mean, you can really do all that. And you can do it accurately.
I can't do that right now. I mean, how hard would it be to go through the program?
It would be boring for everybody because it would take too long.
Okay.
I mean, I could do it in a few minutes, but you don't want somebody just standing there doing stuff.
Okay, we're going to have to cut it off with the formal questions now, and Sam I think you'll be glad to stay around for a little bit for,
You bet.
for any additional questions. But let's give Sam a hand for